Hi everyone, my name is Ricardo Ribeiro and today I'll be presenting the project from my master thesis, which is called DenseFlows, a generative adversarial method to train a model to detect money laundering. This work was done in collaboration with Jacopo Bono, David Aparício, João Ascensão, Pedro Bizarro and Pedro Ribeiro. First I will start by motivating our work, introducing the problem of money laundering detection and covering the main limitations of current solutions. Then I will present our proposed method and the main results of the experiments we made to evaluate it. And lastly, I will summarize the presentation and list different ideas that we want to address in the future work. Let us start with the motivation of our problem. Our goal is to detect money laundering, which can be defined as the process of disguising the origins of illegally obtained money. Typically, people perform criminal acts in order to generate profit for themselves. However, spending these funds directly could attract attention to the underlying criminal activity. As such, this money is considered dirty and they need to conceal its origin before spending it. The money laundering process usually involves three steps. In the placement stage, the money launderer introduces the illegal profits into the financial system, usually in the small chunks in various banks. Then, in the layering stage, the money launderer engages in a series of movements of funds in order to distance them from their source. This can involve transferring money across multiple financial institutions from different countries and different jurisdictions. Lastly, in the integration stage, the funds have already been cleaned and can re-enter the legitimate economy. At this point, money launderers can spend their money in luxury items or invest it in business ventures, for example. In this work, we focus on detecting money laundering during the layering stage. Again, during this stage, the money launderers make several transactions between several financial institutions in order to distance the money from its source. However, this activity is very difficult to detect, given that each bank has a very limited view of the entire financial system. Instead of being able to see the complete graph of transactions, each bank can only monitor transactions that involve at least one of its internal accounts. The money launderers take advantage of this limited view by repeatedly jumping between different banks, such that each of them has as little information as possible. As such, the transactions that are indicative of layering are usually made between accounts of different institutions, like the ones highlighted in bold. We can represent these in and out transactions from the point of view of a single bank as a directed tripartite graph. Here we have a set of external source accounts that transfers money to a set of internal accounts, which in turn transfers it to a set of external destination accounts. The money launderers use these accounts to create a flow of money through the bank. Banks are responsible for monitoring money laundering activity and should create an alert every time they notice something suspicious. This is usually accomplished by encoding the domain knowledge of experts in the form of rules that capture known money laundering patterns. These patterns are usually quite simple, only monitoring a single account at a time, triggering when a combination of different statistics like total amount or number of transactions in a specific time window is above some threshold. The problem is that these patterns are not just simple, but they are also frequently publicly available, since they are based on disclosed legislation. Because of this, money launderers can adapt their behavior in order to avoid triggering the rules. In order to catch these false negatives, we want to construct a machine learning model that complements the rule system we have in place. This model should be able to distinguish between legitimate transactions and money laundering transactions that the rules misclassified as legitimate. However, in reality, we only get the labels of the alerted transactions, because those are the ones that end up being reviewed by analysts. As such, we don't know which patterns of money laundering are evading the rules. Our solution is to use domain knowledge to train a generator to create synthetic money flows that do not trigger the rules but that should be alerted. Then we train a complementary model to distinguish between generated transactions and the real data. This way, we are able to find gaps in our current anti-money laundering solution and at the same time complement it with a new machine learning model. Let us see how we can implement this solution. The three main problems that we need to solve to make this architecture work are: how do we represent and generate transactional data? How to ensure that we create money flows that mimic money laundering and not some other pattern of transactions? And how to make the generator learn to avoid triggering the rules. First, let's see how we decided to represent our data. Transactions are usually represented as a table with several features in which each row corresponds to a transaction. However, in the context of detecting money flows, we conceptually visualize them as a direct tripartite graph, as we have previously explained. To represent this graph, we can use a tensor with three dimensions. The first dimension corresponds to the internal accounts, the second dimension corresponds to the external accounts, and the third dimension to the time window of the transactions, discretized with some time units. Each cell in the tensor contains the sum of the amounts transferred between the corresponding pair of accounts during the corresponding time window. The main advantage of this representation is that we have a fixed size input and output for our models. This gives us the ability to work with dense layers or convolutional layers instead of recurrent units to generate time series. However, we should note that this tensor will be very sparse, meaning that most cells will have a value of 0. This is because we do not expect to have transactions between each pair of accounts every day. Given this data format, the generator architecture becomes very straightforward. The generator receives a random noise vector as input, which will be the source of diversity in the generated data, and outputs a 3D tensor representing one example of money flow as we saw before. The architecture can be split into three sequential blocks. In the first block, we increase the size of the input vector using dense layers and reshape the final layer to be in the 3D tensor format. In the second block, we further increase the size of the time dimension using transposed convolutional layers. In the third block, we perform a categorical sampling step in order to make our output tensor more sparse. Using this setup, we can generate data in the intended format, but how will we teach the generator to create examples that mimic patterns of money flows? Well, we know that money flows are characterized by similar total amounts of money going in and out of the internal accounts. As such, we want to avoid situations where money is blocked or created by the internal accounts. To measure how well a graph or a 3D tensor is presenting this behavior, we use this loss function. We reward our model as the amount of money transferred increases, but penalize it if the total amount of money received and sent do not balance. Beta is an hyperparameter that allows us to tune the relative strength of the balancing factor. Besides making sure that the generated data consists of good examples of money flows, we want to ensure that the generator learns to avoid triggering the rule system. Since the generator is a deep learning model, it needs a gradient during the backward pass in order to learn. The problem is that simple if-then rules cannot give that type of feedback. Our solution to this problem is to substitute the if-then rules with another deep neural network, which is trained or engineered to give the same answer as the original rules. The key difference between them is that the proxy network is differentiable and as such can give meaningful feedback to the generator in the form of a gradient. Now that we are able to generate examples of money flows that avoid triggering the rules, we can train our complementary model, which we call the discriminator. The discriminator receives either a real or fake example as input and should learn to distinguish between them. Again, the architecture can be split into three sequential blocks. In the first block, we reduce the size of the time dimension using convolutional layers. In the second block, we perform a set of aggregations that ensure that the discriminator is permutation invariant in relation to the order of the accounts. And in the third block, we reshape the 3D tensor to be a linear vector and reduce its size to 1, which will be the output using dense layers. Here we show a diagram of our complete architecture. We have our generator that will create examples of money flows which will be trained with feedback from the rules proxy, which will teach it to avoid triggering the rules, the money flow objective, which will incentivize the generator to produce examples with the desired behavior, and the discriminator, which will be our complementary model to the rules, trained to distinguish between real and generated data. We combine the feedback from these three sources using this loss during the training of the generator. We use hyperparameters alpha and gamma to tune their relative strength. Now that we covered our architecture, we will see some results we got from testing our method. The dataset that we use for the experiments is an internal dataset from Feedzai. After gathering the relevant transactions for this project, the resulting dataset is comprised of 200,000 transactions made between 100,000 unique accounts spanning over 10 months. First, let's compare the distributions of real data and synthetic data. Because we include the money flow objective in the loss of the generator, we should expect a larger volume of money being transferred compared to the real data. Looking at the distribution of the amount of money flowing through the internal accounts, we see that clearly the generated data has higher amounts of money flowing than the real data. Looking at the distribution of the amount of money transferred per transaction, we see that the generator is not creating larger flows by making significantly larger transactions. This could be somewhat expected, since making transactions with much larger amounts would start to trigger the rules. The reason for the increase in money flowing is that the number of transactions is much higher in generated data compared to real data, as we can see in this third plot. It is important to note here that even though the amount of money flowing is much larger, our generators are virtually never triggering any rules. We are also interested in investigating the performance of our discriminator. Can we use it to complement the rules? Here we show a distribution of the area under the rock curve on a test set for many discriminators trained with various hyperparameters. We see that many discriminators have an AUC close to 1, meaning that they are good at distinguishing legitimate from generated examples. The last experiment that we are presenting here is an ablation study. Here we show the effect of removing the money laundering objective from the architecture, and as you can see, the amount of money flowing follows much more closely the distribution of real data, meaning that the objective is crucial to mimic suspicious money flows. If instead we remove the proxy network, we see that the amount of money flowing becomes much larger. However, this happens at the cost of triggering the rules almost for every transaction, which means that this would be a very bad money laundering strategy. Nonetheless, it indicates that the rule proxy network is needed to avoid triggering the rules. So this concludes the results I wanted to show. I will now give a summary of the work we did and possible directions for future work. We saw that current anti-money laundering solutions are mostly based on simple rules that are publicly available, which is something that money launderers can learn to avoid. Our goal in this project is to improve the detection of anti-money laundering systems by capturing more complex patterns of money laundering that are not captured by the current systems. Our method learns to generate examples that finds gaps in the current solution and trains a model to complement it, fixing those gaps. From everything we did so far, there are several changes that we can explore in the future. For example, right now we are just using a very small number of features, and we know analysts use much more in order to decide if some activities are suspicious or not. For example, the country of origin or destination of the transaction. We can also change the money flow objective to encode other money laundering patterns. So far we only explored one specific pattern, which is the money flow, but there are several others that we can try. We saw that the distribution of real and generated data are quite different and easily distinguishable. We probably don't want our generated data to follow exactly the same distribution as real legitimate activities, but it would be interesting to try different degrees of realism and see how they impact the performance of the discriminator. Lastly, we have been studying how this could be applied to other domains, like fake reviews in e-commerce or propagation of misinformation through social media. Thank you for watching my presentation, and goodbye.